The first speaker this afternoon is Jorge Lopez-Abad from Madrid. He's going to talk about approximate Ramsey properties of matrices and finite dimensional non-spaces.
Okay, thank you very much. So do I wait a little or not? I don't wait because they are entering. Well, I can start. Well, as it says the title, I'm going to talk about that. For those who were here 1 month ago, I gave a talk with something very similar to that, so I apologize for that. I thank the organizers for this opportunity. And that's a joint work with Dana, Martino, Lupini, and Brice Mombo. As a matter of fact, this started with just Dana and Brice Mombo, and then we incorporated Martini for some applications of these techniques, which I am not going to discuss today, which is essentially about non-commutative world, whatever it means. So, but now I'm going to talk about simple things, I guess. Matrices, everybody knows what is that. So this is the outline. I will explain first what is the result for, which is well-known result, well-known, somehow well-known, on matrices over a finite field F, which of course has to do with the dual Ramsey theorem. And then I will go to our result, which is about the case where you deal with real numbers or complex numbers, even rational numbers. Even I don't discuss about them, but it is the same kind of idea. And I will point out some of the results about Grassmannians over real numbers or complex numbers. And then I will try to convince you or try to explain you how the proof goes. So, which is really number 2. The point 2 is the key point. Is the approximate Ramsey property of finite dimensional norm spaces, whatever it is. I will say what it is. And the more specific case where the spaces are so-called polyhedral or polytope spaces. They are called polyhedral, but they should be called polytope, I think. And as I said, the very particular case of L infinity n's, these are the universal polyhedral spaces, and this case is really the key. Well, I will reformulate it if I have time, the same result a la Borsuk-Ulam. So maybe you are more used to that than to the Ramsey properties. And it is, I think there is a very nice open problem in there, as far as I think, that I will also discuss, and then I will pass very fast about what else you can do with this kind of techniques, and what else you can do, infinite matrices, and things like that. So I will start with standard notation or simple notation. Matrices over a field F is a field, which will be at the beginning will be a finite field, but soon will become real numbers or complex numbers. But for the first part, F will be a finite field, and M, N cross K, these are the all matrices N cross K matrices over F, where the entries are in the field F. There are special ones, which are those who represent embeddings, and these are the matrices N cross K, matrices of rank K. So they represent injective things, okay? Injective embeddings, I mean. And then of course there is this GLK, which are the invertible ones, so K cross K. And then there is the Grassmannians, because we will have some application about the copies of things, not just embeddings, but copies of things, which is usually called K Grassmannian, which are the collection of all the k-dimensional subspaces of a given space V, excuse me. Or in this combinatorial way, these are the copies of Fk on V, and copy means obvious thing here, right? Here there is no norm, there is nothing, there is no distance, there is no metric. This is exact. Okay, so what I really enjoy about that is that the argument is the strategy of the argument. I think is rather clean, and it uses elementary things, which I think everybody knows, or maybe they remember once they working with that. And these are these reduction, this decomposition given a matrix like that, and it's injective, so the rank, so this is A, and the rank of A is equal K, exactly K. There is this nice decomposition which is called this reduced column echelon form, which is what? So you have A, and this is a multiplication of what? Of matrix which I call it red A, which is in reduced column echelon form, which if you remember is something like that. I am not going to enter into the definition, but there are many zeros here, and there is a 1 here on the left, and then there are many zeros until here there is a 1, and here I don't know, but here there is a 0, there is something here, here 0, then there is another one here, another way 0, and so on. And this always exists, right? This in the other form, in the row form, this is used to solve linear equations and things like that, right? This is how you do it. Well, any A is a multiplication of red A and tau A, where tau A is an invertible matrix K cross K. This is rather simple. Among them, there are those who are already in reduced row, reduced column echelon form. This I call it E n cross K, because in the case of real numbers or complex numbers, there will be exactly the same thing. It will not be that, it will be something else, because it doesn't, you cannot do the same, but it will be something else like that. So very specific A's, which are very specific properties. Okay, so this is the theorem who's telling you how the colorings, arbitrary coloring of the matrices, full rank matrices look like in a Ramsey sense, right? So if you have any, well, again there are these always parameters, K, M, and R, these are integers, so there is a big N, so that whenever you color the full rank N cross K matrices over F into R many colors, there will be a very specific matrix R, which I call it R because of Ramsey matrix, and there is a reduction of the color F to this coloring of the invertible ones, so that you know exactly what is going on with F in the right place, which is, okay, this one, right? So any coloring of a guy who is of the form R times A, this coloring will depend only on the tau of this A. And I remember that the tau, I remind you that the tau is this thing. So modulo this specific one, the remainder, something like that, right? So it will only depend on that. So, okay, how do you prove that? Well, okay, yeah, this is an easy consequence now, because this is, as always, when you have a result about embeddings, you have result about copies. Copies is always way more complicated, the other way around. Embeddings is way more complicated than I don't know what I said, but I want to say that embeddings are more complicated than the copies, because there are kind of automorphisms there, right? So, but as a consequence, since every subspace W is the image of a matrix in reduced column echelon form, if you apply this thing, you will always get in this part here, you will always the identity. So you have that for every K and every M and every R there is an N, so that whenever you color the Grassmannians, K Grassmannians of Fn into how many colors, there is a V, a subspace of dimension M, where the coloring is constant on the K-dimensional subspaces of V. Because you always have the right to choose your given V, to see your given V, your given W as the image of some good A. Okay, so this and the other result is a consequence of the dual Ramsey theorem, which was already mentioned before by Dana, and which says the following in this way. Dual Ramsey is about partitions, blah, 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 right? Like the Ramsey is about the sets of certain size, but it's easily seen to be the same that for linear orderings and embeddings between them, and the dual Ramsey corresponding interpretation is that. You have two linear order sets, S and T. They are finite typically, but the definition is in general. And a surjection from S onto T is called rigid when so you take T0 and T1 on the image T, you take the pre-image by the theta, and the very first element must come before the very first element of the other one, if T0 is smaller than T1. Is it clear? I always choose as a pre-image a guy which is coming before than the other guy which is going to go to T1. Okay? And then I don't know. Then they can switch, they can move around, but the very first always come in this order. I'm going to use this notation APST as the collection of rigid surjections between S and T, and then the dual Ramsey states the following, that if you have a finite linear order set S and T, then you have a number of colors R, and then there is a big N, so that whenever you color with R many colors the epi from N with the obvious ordering, with the canonical ordering of N onto S, you color with R many colors, there is a monochromatic set of the form. There is there is a rigid surjection from N onto T, so that whenever I take this sigma because again sigma is, well, it should be in rho. This is wrong. It should be rho, but okay. So you take the sigma and then you compose with any rigid surjection. The composition of rigid surjection is again a rigid surjection. So any of these compositions has the same color. This is what it says. Well, I wrote down, I typed the proof, which is almost complete because it's rather simple once you get the point. Okay, so not the proof of the dual Ramsey, but the proof about the full rank matrices, yes, using dual Ramsey. Yes, okay, so dual Ramsey is about orderings and rigid surjections. So the very first thing you have to invent is some ordering there. Well, how do you do that? Well, you fix your finite field F and you put an order on F, which starts by the 0, then the 1, and then arbitrary. Well, this is a very special number. This is not so special, but it is special in my context because of that. In this reduced row echelon form, after 0, there is a 1. But I could have here another number, but I decide always to have this one. So that's why I put here that the 1 comes after, it comes right after the 0. And now, okay, so now I have to invent a device. I have to invent an algorithm who are given an epi from N onto F to the K, it will give me a matrix, full rank 1. And how do I do it? Well, if you write down what it says in there, it's rather simple. It's simpler than what it says there. So how do I call it? So I have a sigma, this is onto, and now what I have to define, I have to define that, right? There is only one choice. I have a given integer here, I less than n. Well, I can compute that. This is a string, k string, right? So I just put it there. This is the most obvious choice. And it, okay, and this is well defined because there is always the 1 there, so you check that this is well defined, so this is a full rank. There is no problem with that, okay? Okay, so what is doing this thing? It is putting all these values in fk in a random way in respect to this sigma, putting many repetitions, many places the same, so that it will work. You can use dual Ramsey, as I will see, and you will get the result. So okay, so maybe it's a good idea if I write down here what the result is, so that you can follow what is the strategy. So I have inputs k and m, number of colors r, and I want to find n, so that if you have a coloring here in r many colors, I have to find some r in this reduced row echelon form, so that, and I have to find some g from the invertible ones into r, so that you have the following. You have the following factorization. So you want to find this, and you want to find that. Yes? Okay, so how do you do that? Well, enlarge the number of colorings, as always. This is what I am doing there. So, well, you are applying the dual Ramsey theorem for whom? For this order set, as I said before, anti-lexicographically ordered. For this anti-lexicographical order set, this is S and T, and this big number of colors, because at the end of the day I want to find this G. G is a color in there, right? One of the typical colors in there is one of these G's, right? It's mapping from here to here. Okay, now this is the end. And how do? You fix your given coloring F, as written in there, and now I'm going to induce a new color of this epi from N onto Fk, which is simply the composition. So what do? I have this phi here, and then I multiply by b, any b which is in there, and I compute the color F. And I do it for all the b's. Yes, so this is a coloring really onto here, yes? Given the F, it will induce this coloring there. And now, by the dual Ramsey, there is some row epimorphisms from N onto Fm with the anti-lex ordering, so that C is constant in all these compositions. If I make any composition of this kind, I know that this will always be colored by a value which I call it G. I call it G because it's this G there, right? Okay, so now let us see why this. Okay, and now, well, maybe it's a good idea that I remind here. So there is this row no, N, and there is this G. So let us keep this in mind. Well, given a row, I have the corresponding matrix R. Yes, so I have that, exactly as I said before. And if you think for a while, since rho is anti-lex preserving, this R is in reduced row echelon form. This is easy to verify. And now, what is the key? I want to control, as it says in here, so I want to know what is written here is exactly that is the diagram here is commutative, right? So I want to know that, which is what is written in there. Okay, so you fix an A, you decompose it, and now you simply multiply the things, R on the left, and R, I remember that is phi of this rho, so I simply put it there. Well, it is rather easy to see that since ret A is in reduced row echelon form, well, I am thinking now this is now a matrix, so this is a little abuse of, so this is a matrix like that now, because I simply take the transpose, and I'm considering this as an epimorphism from Fm onto Fk, which is simply the multiplication, right? Given some B transpose of some given vector x is simply the multiplication, yes? And it is not complicated to see that this preserves the anti-lex. I mean, this is a rigid, not preserved, excuse me. It is a rigid surjection with respect to the anti-lexicographic, because ret A is in reduced row echelon form. This is a very nice where the zeros where they have to be, the ones where they have to be, and you simply think, make little computations, and you get convinced. And it is also easy to see by definition that when I have this multiplication there, this is simply to take, so now I verified somehow, I convinced, I hope, that this is a rigid surjection. So I have the right to multiply, to compose rho with another rigid surjection. Again, this is an abuse of language because this is a matrix, but I mean that. So, and if you put what is this and what is on the right and what is on the left, you really see that this is the same thing, exactly the same thing. Okay, so maybe I have to put it there. Well, now you simply put all the things together, and the key is this part here. Now this multiplication became rho composed with sigma and then the phi multiplied by the remainder, and if you see how I define the color is C, this is exactly the coloring of this composition applied to this invertible matrix, and this is by the Ramsey property of rho. This is G of tau of A. It is really more easy than maybe now going through track all this. This is really a simple, very clean argument, I think. Well, this is about the minimality, because once you have these kind of results, you want to know that they are unique. Because what this tells you that, so what, maybe you are using here too many colors. You can reduce the number of colors, but it is rather easy that you cannot, because this is a bad coloring. This is a coloring who will use, any place will use this number of colors, so you cannot reduce. This is the Ramsey degree. Okay, so this is the argument I'm saying there, but I will not go to this. Okay, now what happened? So this is the result for finite fields. I think is rather clean. The strategy is rather clean. The arguments you are using are basic things in linear algebra, and there is a non-trivial thing which is the dual Ramsey theorem. This is the really non-trivial part, and as a matter of fact this is really complicated, because this is more or less dual Ramsey implies any other, I am exaggerating, but most of the other Ramsey principles. This is really very strong. Now what do we want to do? We want to do exactly the same thing for real numbers or complex numbers. Well, there is a very first problem, is that there is no result like that, because R is infinite, or C is infinite, so you cannot do it. So you might say, okay, I stop, bye-bye, see you later. Well, yes, I could say that, but you can do something if you allow to make little errors. Yes? So what you have to convince the next thing is that you must use little errors all the time. In a controlled way, of course, because if you don't have control about the errors, you can't get anything, right? And we don't want that, I guess. Okay, so these little errors means that you have to put a metric on the matrices. You have to put a metric. You have to tell me, you have to know what it means. This is close, this is not the same, but it's quite the same. And of course now there is a, here I choose this matrix norm, but I can use many other matrix norms. I am choosing this one because this is a new result and it has new consequences which about some Banach spaces and this extreme amenability of some groups, well-known groups. But you could have used there another one, right? Not the infinite, but the 2 or the p. And I think this is just about that as far as I know. Okay, so good. This was the Ramsey degree, right? So to any matrix you have this nice, you take A, you put it in this reduced row echelon form, you take the remainder, and this is what it represents. Any coloring somehow, yes? And the G, of course. What is the equivalent now? As I said, I could do the same, but then they have a big problem about the errors. This decomposition here do not respect this distance, meaning this might have a very small norm, this might have a huge norm. No way this can work. Well, instead, the key, the corresponding set Ramsey degree is that. The set of all the norms from Fk, K is F is real or complex numbers, doesn't matter, and all the norms you can imagine, this I call it Nk, and that's going to be the Ramsey degree, metric Ramsey degree. Well, I put here 2 examples because these are the ones well known and they are somehow very canonical and they are easy to explain, right? So the sub norm, which is a key on this, but also you could use the p norm. I am going to use this notation n infinity or np because I will use many m's and n's, and so I think it's more convenient like that. Well, okay. One thing which you have to think, the next thing you have to think is that this nk is not compact. It is not finite as this was. This was finite, so it was the very nice, finite things are nice. But this is not even compact, so you have a problem because at the end of the day you will have to approximate things and you need some kind of compactness to approximate. Otherwise you don't know what to do. Well, that's why I put these intervals in there because, well, given 2 norms m and n, I write m is smaller or equal than n if and only if it is pointwise smaller or equal to. Okay, and then there is this interval of all the norms which are between m and n, and then there is this little observation that this is exhausting everything. If you take any m and you take a and b and you run a to the 0, b to the infinite, then the union of all these intervals is going to be all the norms, because any given norms, 2 norms in Fk are comparable. This is what it says by compactness. Yes, the balls are compact.
What does this thing is missing?
What did I?
The union.
Well, this is Nk. The union of this is Nk. Let me write it down here. Yes, this. It doesn't say anything. You are right. Well, it says one thing, but not what it should. It says nothing. Yes, yes, I agree with you. I didn't say what is that, but you can imagine what it means that, right? Okay, this is better, right? Okay, so metrics. I said that now it's about errors. You must allow errors, otherwise there is no Ramsey on that, any kind of Ramsey. So metrics, there are many metrics in NK. Okay, there is one which is very baroque. I will think on that, but it's very convenient because of the numbers, the ellipsis constant that will show up, they are the best, which is this one. I will explain you in a while what is that. And there is one which is not so baroque. Okay, there is this log here, but if you forget this log here and you only take maximum between these two values, maybe I'm going to write it down there so that you have it in mind. Well, and I will write it in the general way. So there is a norm P on Fk, and now you have another one. This is fixed. And now you define the norm. Did I put, well, D0? It should be G, because it's geometrical. It should be G, so I'm going to use G. This is the 0 there. M and N. What do you do? Okay, so you have P. You have unit ball of Fk with M. This is a compactor with respect to P. This is a given metric. I have a metric, well, metric d dw is P of V minus W. Yes, this is a given metric in the ambient space, and you have two compactor, this one and this one. And then I take the house door. So it's the house door distance with respect to P. This is in the ambient, and these are these two compactors. And now, again, what I'm doing in there is to put here P as L1, and instead of seeing what is the distance between this ball and this ball, I take the adjoints, the dual norms. Okay? This is again because of it is convenient for the ellipsis constants. That's it, but it is the same idea as I said here, right? So this is this is a geometrical way of comparing M and N. You have this ambient P. You have the balls with respect to the unit ball with respect to M, unit ball with respect to N, and then you take the house door distance with respect to P. And then there is this D1, which is, I call it indeed O because of operator, which is an operator norm, right? So what is given an operator linear map? This is finite dimensional. I can do it, of course, in the infinite dimensional in general, but this is always finite dimensional. So I'm going to just consider that. So I have this. I'm going to put it in very general form. And what is the norm T Mn? This is the maximum of what? So you take M of x less or equal than 1, indeed 1, it doesn't matter. You compute T of x, and then you compute N of this. This is definition. So what I say in there, well, I take the identity from Fk with M to Fk with N, and I compute the norm, and then I compute the inverse, which is the identity again, and then I take the maximum of the two, and this is the other distance. Yes, well, this is multiplicative. So distance, as it is in there with this, without the log, if I call it this rho, this is less or equal than and that's why you put log here, and then it will be additive. Okay, log in there is simply to make it an additive as usual metric. Otherwise, there will be multiplicative because it's composition. Okay, so there are these two distances in there. Well, good, I wrote everything. This is what I said there, okay? Well, as I said, NK is not compact, but all these intervals, I didn't write it down, but all these intervals are compact. This is very good for us. Now, there is a relation between these two D's, DG and DO, or D1. There is these two relations which depend, of course, where M0 and M1 they are seated between the infinity norm. Why infinity? Because I will not go to the details, but in here there is L1. L1 is the dual of L infinity, and that's why it shows up that, okay? Without entering into too many details. Okay, now, here I told you how to find the tau. You take this decomposition and you take the remainder. This is tau. What is tau now? Well, you have a matrix, and then, yes, so maybe I'm going to put it here. You have a matrix, full rank. So, and now what is tau infinity of A? This is in NK. Well, I know I am always having under this subnorm, which is in Fn. I have it here. So I have a way to go from Fk into Fn. This is injective. The multiplication by is an injective because it's full rank. Well, I can define tau infinity of A of V, a single V, given V, to be simply going by A, by multiplication I am there, and then I compute the subnorm. And that's the definition. This is the tau. Okay? So it's a very canonical, and again, I commit myself from the beginning the infinity, but you can do the same with the two norm, with the P norm. And then the proofs are another story. They are not the same, but okay. And now, what is this E? Remember, the E before were these special ones, which are those, and in the previous case were those who are in the reduced row echelon form. Well, now they are those for which, when you pull back the infinity, the n infinity, you put it back to Fk, you get n infinity. Are like the very fixed points of this. Like with this reduced row echelon form, they were the ones so that when you make the reduction, you make this decomposition, you don't do anything. Yes. So okay. So in human language, A defines an isometry between an infinity k and infinity n. But I am trying to convince you that there is a similar path from in the finite field and in this one. Of course, now it's another story. Okay, now, well, these are little observations. Is that this is one ellipsis with this d0. If you put here the d0, the one which was bizarre, which was this house door distance with respect to ambient L1, and then the dual of m, dual of n, the ball, blah blah blah. Then it's one ellipsis. You get one here. That's why I introduce. And if you run now, you fix k and you run n, and you take the tau, you get almost all the elements of nk, all the norms, up to epsilon, and epsilon can be as small as you wish. That's the result. Well, this is a version. It is a little stronger than that, which will come in the very next one. And it says the following. So for every, again, there are these parameters, right, as before. So before there were k and m, and there was the number of colorings. Now there is k and m. This is because of what I said, that this is not compact, so you have to make it discrete, and that's why you have to take some intervals in here. This is the error, and this is kind of the coloring. This is R before. Yes? So it's a very similar. Okay, so there is some integer n, so that whenever you have ellipsis coloring now with real numbers, again I said I put the real number, but you can do it better than that, just to clarify the kind of result we obtain. With ellipsis constant, so this is like to say at most are many colors. Now this you say the ellipsis constant is at most L. Then there exists a special R, Ramsey matrix, which preserves the infinity norm. This is what it says. And there is a G from NK, all the matrices, to R, with ellipsis constant a little worse than the given one, I mean, little worse than L, yes? So that you have this factorization as before, the same than here, except that now, of course, we are living in the world of the error, little error, so up to epsilon. This means that if I go this way and I go this way, it is not quite the same, but the distance here is less than epsilon. This is what it says. So it's a very similar result, yes? Okay, so, well, as I said, as it is presented there, this is not the strongest result is more than that, and well, so you can replace R by L infinity n's and more other category, other spaces, metric spaces, but I am not going to enter into that. Doesn't make any sense. Okay, but what I want to say is that when you put L infinity s of R instead of real number, which is L infinity 1, then you control all the finite colorings, because really discrete coloring. So this is the case where you are obtaining discrete coloring, because if you have a discrete coloring with R many colors, you can define an ellipsis which encodes that very easily, right? So you have that. R is an integer now. So you can define distance to, so given a matrix here, you can define f of A to be the distance to the pre-image of each of the colors. This is now a string which is living, so this is a set, right? Yes, and this is a string now who lives in an infinity number of colors R, and you convince very easily that this knows C and vice versa. All the information is in here, in this F. This is one ellipsis. F is one ellipsis. Okay? So you control the colors as before, but you control more. Well, there is a uniqueness, as I said, something about the minimality. Of course, now you have to be careful on the things, what you mean by unique, but there is a way to really express mathematically what you mean by unique, but I'm not going to go through. Okay, now very fast, what happened with the Grassmannians in this case, right? We know about the injective, full rank things, matrices, and now what happened with the Grassmannians. We want to know what happened with the Grassmannians, with the copies. Well, again, there is, you must have an error in your hand, otherwise it will not be true. There is nothing to say. So again, as before, I have to put in this set distance. I have to declare what is the distance between V and W. And again, this is a very natural thing, as I explained before. You have two k-dimensional subspaces of Fn. You take the unit balls of V and W with respect to fix one ambient distance, which is an infinity. These are compacta. You have this ambient infinity distance in Fn. Now you compute the house door distance between these two compacta, and this is very natural, very geometrical, and that's the good one. Okay, now, what is now here? I want to have here this kind of thing, right? This is K. So I want to have the same thing. Who is this? Who is that, right? Well, it's a well-known thing. This was a nice surprise. This is a very well-known thing and study, complicated thing, which is this, what is called the Banach-Mazur compacta, which is, it is nk mod out of pseudo distance equal to 0. And what is this pseudo distance? Well, it has to do with this geometrical distance, operator distance d1 I said before, except that in that case I was only using the identity, yes? And now, of course, now I take any invertible matrix. Again, there is this thing here to go from multiplicative to additive, but this is not important. What is important is what is in there. I can move M anywhere I like with this invertible thing. I move it. I compute now the identity, which is what it says there in some baroque way. It is the same as before, except that now I can move M and N by an invertible thing. And then I compute the best possible scenario. This is the pseudo distance, Banach-Mazur pseudo distance between M and N. This is not a distance because this is equal to 0 if and only if there is an isometry who moves M to N. Okay? So, for example, N infinity and 2 times N infinity are the same. They have a distance 0 because you can take the matrix which is 1/2 and then the identity, and this moves 1 to the other, or 2, I mean, maybe 2. As I said, is 2, right? 2 times the identity moves 1 to the other, and they are not the same. But they are isometric. Now this is a compactor. That's why it's called compactor, right? And now, what is the tau? Well, it's new now. I don't know why. New norm, maybe? Well, you have a V, a k-dimensional subspace. You have V, you have the infinity norm, and you compute the isometry type, like in model theory, kind of. What is the type, isometry type of this? Okay. More precisely, if you want, you take any matrix A, full rank matrix whose image is V, you compute the tau infinity, and then you compute the class with respect to this equivalent relation I just said. Okay? Well, this is ellipsis, and the ellipsis constant just depends on k. This is a little computation. This is not so complicated, but in any case, so this is the result. Now the things are different than in the, well, somehow different, but they might be more or less the same. In the previous case, this Graham, Lieb, and Rothschild result was saying that there is a subspace where the Grassmannian, where the coloring in the Grassmannian is going to be constant. In here, you can have just the opposite. In what sense? Well, given k and m and epsilon and n, there is some integer n, so that you have ellipsis coloring with ellipsis constant almost L of the Grassmannian on real numbers. Again, this can be more than real numbers, but there exists some V, which is a special one, and this is the special thing, isometric to infinity L, and there is a way to, and you are going to make a factorization of f through the Banach-Mazur compactor. So f will only depend, up to epsilon of course, on what is the value of the, what is the class of the subspace you have in here, the Banach-Mazur class. This is what it says, right? Okay, so this will not be constant because this map here, when v goes to infinity, the dimension, excuse me, the dimension of v, which is m, goes to infinity, you get almost everything on here, dense. So this will never stabilize if v is this special. But, well, okay, so now maybe what Hilbert space has of different than the others? Well, one of the things which characterize the Hilbert space is that any subspace of a Hilbert space is Hilbert space. Is isometric to the Hilbert space of the corresponding dimension, linear dimension. This is unique on the Hilbert space, which means that if you think for a while, imagine that I can get that where V now is going to be with the infinity norm, the isometry type is L2 of M. Well, then this assignment here will give me always any k-dimensional subspace, will give me again L2k, the isometry type of L2k. So I will have always the same point here, which if you think, what it says is that the f, oscillation of f, will be less than epsilon. Because I always get, this is constant. If this is constant, this is almost constant, right? This is what I'm saying. So this is the content of what is written there. Since the L2 ends are universal, almost universal, up to epsilon, I can imagine that the V, my V with the infinity norm is L2M, and therefore I get the corresponding result like Graham, Leib, and Rothschild that says that you have a ellipsis coloring, blah, 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 then it's going to stabilize somewhere. Except that now this V is not L infinity, it's L2. It's not L2 because it cannot be, but it's very close to be L2. Yes, but that's very clear, I think. Well, okay, so in the last 5 minutes or 3 minutes, I'm going to go very fast. I prepared too many transparencies, or I talk too much, I don't know. Okay, so the key on these matrices, all these results on matrices and some others I didn't present is that this property here, which is the approximate Ramsey property of a family of Banach spaces. And what is that? Well, this is like this structural Ramsey property, except that now it's not about the copies, because if you remember, Dana in the morning was saying many, many times rigid structures. Because really the dynamics is not about the structures and the copies, it's about embeddings. The dynamics is about embeddings. Of course, if you put rigidity, embeddings and the copies are the same. Okay, so, well, so approximate Ramsey property is about embeddings, and it says what it has to say. You have this F and G and K and epsilon, there is some A, so that, well, this is non-triviality, but what it says is you have ellipsis mapping from all the embeddings. I will not go to the definitions, from F into H, with ellipsis constant, blah, blah, blah. There is an embedding from G to A, so that any composition has, you compute F, and this is almost constant. This is what it says. So this is the Ramsey property, what I call it, or what is called the approximate Ramsey property of the family F. Well, what we prove, these matrices stuff, and a little more than that, is that the class of all finite dimensional norm spaces has the approximate Ramsey property. And this is a little comment that once you know embeddings, you know the copies. This is again the same philosophy, and this is clear, right? So this is what is the consequence about the copies, about the, well, I will not say Grassmannian because this is something else. Okay, and very fast, this proof here is a consequence of the approximate Ramsey property of the polyhedral spaces. Polyhedral spaces are rather easy to see how they are. Yes. It's rather easy to see how they are. This is, you take the unit ball, and it's not like that, as I simply said, but there are many peaks. Yes, this is polyhedral. I will not enter into the details, but this is what it is. So Hilbert or LPs, this is not. This is too smooth. It's just the opposite. There are peaks, like a cube, like the unit ball of L infinity n. Okay, so what is really in the core of this result and the injective matrices and the matrices, which I didn't mention, is the Ramsey property of approximate Ramsey property of the polyhedral spaces, and more precisely, that's the key. So this is the result. Matrices who represent isometric embeddings between infinity n and have the approximate Ramsey property. Well, this is, well, very fast again. Polyhedral, why they are important, relevant? Because you have this norm very smooth, and now you take many peaks on there, on the sphere, you take the convex hole, and you can imagine that the Banach space defined by this and by this other is more or less the same, right? You can approximate any finite dimensional Banach space, norm space, by a polyhedral one, by choosing many, many peaks. This is what it says in there, and then it says something that you have to deal with errors again, and epsilon isometry must be close to an isometry, and things like that, blah, blah, blah. You can do it. Two consequences that were mentioned in the before is that then you have this Gurari space. The Gurari space is like the Hilbert space for Banach spaces. In some precise, very precise sense, it is the case, right? So what you get is that the Gurari space, you take the group of isometries with the point-wise conversion, and this is an extreme amenable group, has this very strong fixed point property. And dual, there is this pulsar simplex, whatever it is, and then if you take the group of affine homeomorphies of the pulsar simplex, this is the universal minima flow is P. Well, I guess I have 1 minute. You can get the same thing with other P's, not just with infinity. You can get it with 2 because of Gromov-Millman result about the unitary group, and then reinterpretation of the extreme amenability in terms of the Ramsey property. Remember, well, now it will be in terms of the approximate Ramsey property. There is a clique also, and similarly for the LPs with P different than 2, different than infinity, by this result of Giordano and Pestov, which is simply by this Banach-Lamperti result telling you how an isometry of capital LP look like. This is well known, and by using this they know that this is extreme amenable, indeed more, and then you have the approximate Ramsey property. And I had the intention to convince you that there is also a very nice reformulation with a la Borsuk-Ulam, but I have no time, maybe you can read something. But there is some nice thing, well, I know that this is too much, I am asking too much, but there is a really nice reformulation using this, not really the Borsuk-Ulam per se, but this Lusternik-Schnirelman reformulation about coverings. And if you think for a while, this is what you are doing about coverings, except that Borsuk-Ulam says something where there is whatever without going into details. It's saying that if you have many of these open sets, then you will have two antipodal points independent of the epsilon. The result you obtain, the approximate Ramsey property of the L infinity ends is exactly Borsuk-Ulam, but there is a dependence on the epsilon, and it is a nice, and it is really what it is the same, and there is a nice thing which we didn't think too much on that, but I think this is a very nice project. You can you have the same kind of result for you don't want to find any more 2 antipodal points, but now you are coloring embeddings, isometric embeddings, and you want to have the similar obvious result in m dimension. Okay, thank you very much.
Thank you. Well, a very short time for questions or comments.
Could you put back the definition of the ARP?
Yes. I didn't say what is meaning. This is metric space. How? I mean, I didn't say, but this is the obvious thing in this context. I mean, with the natural metric model.
Any more questions? No? Then let's thank for the game.